In this video, we're going to talk about series, infinite series, and partial sums. So to motivate that, let's look at this example, which I did in a previous video, of a ball that is thrown up and reaches a height of 20 feet, then bounces, and it bounces to 0.8 of its previous height and continues in that way, bouncing to 0.8 of its previous height. So if we look at this as a sequence, we have our first height, which is 20. Our next height is 16, 12.8, 10.24. And it goes on like that. All right, so that's a sequence. A series is the sum of the terms of a sequence. So an infinite series would be adding up all the infinite terms of the sequence. So the infinite series associated with this sequence would be 20 plus 16 plus 12.8, etc. forever. Now in the last video we talked about the formula for this. H sub n equals 20 times 0.8 to the nth power, where n is 0, 1, 2, etc. So we could write this as a summation from n equals 0 to infinity of 20 times 0.8 to the nth power. All right, and that would be that infinite series. Does that have an answer? Okay, that's one of the big questions we're going to be asking. If I add all these numbers together and I keep going, we know the numbers are getting smaller. The numbers are getting smaller, but I keep adding more numbers. So will that go to infinity, or will it ever get to be more than 200? I know I've got 36, 46, 48.8, and the next term is 10, so 58, and it's about 59. Will it ever reach 100 feet if I keep adding up all these numbers? Okay, that's some of the questions that we're going to be asking. A partial sum is not adding up all the terms, all right? Partial is the key here. We're only going to add up a part of the terms. I was going to say some of the sum. So the partial sum is denoted with a capital S, and the subscript tells you how many terms you're adding. So the partial sum, S sub 1, is just 20. S sub 2 would be adding the first two terms, which would be 36, is the next partial sum. All right, the partial sum of 3 terms would be that value. So 36 plus 12.8 is 48.8. So you can see the partial sums themselves are creating another sequence. All right, so if I look at the partial sums, the first sum is 20, the sum of the first 2 terms is 36, the sum of the first 3 terms is 48.8. Let's do one more. The sum of the first 4 terms would be 48.8 plus the next one, 10.24, which would be 59.04. So if we keep doing this, and we did this forever, the sequence created by the partial sums, if we ask ourselves, does that converge or diverge? Can we somehow determine that? Then we're getting the answer to this question. If this sequence converges to some number, that number is the sum of the infinite series. If this diverges and keeps getting bigger and bigger and bigger, then this infinite sum does not have a solution. Okay, so that's a little heavy. Let's think about that. The partial sums create a sequence, and we want to ask ourselves whether that sequence converges or diverges. Because if that sequence converges, then we know the infinite series will also converge to some number. Right? Spend some time thinking about that, or maybe saying that back to yourself. That's a big concept that we need to get our minds around. So with all the math symbols, basically what I just did on the previous screen is summed up in this definition. right? Given a sequence of terms, the sum of its infinite terms can be written like this. It's called an infinite series. The sequence of partial sums associated with this series. So here, again, we're creating a sequence. What's the difference between a sequence and a series? A series is all the numbers added up. A sequence is a list of numbers. So this sequence is a list of the partial sums. S1, S2, S3, Sn. Okay, so this is a good way to think of this. This sequence, S sub n, is S1, S2. Notice I'm not putting pluses in here. This is a sequence. How do I get the numbers in this sequence? I add up a certain number of terms in this series. Okay? So the S sub nth term in the sequence of partial sums is the sum of the first n terms, which can be written as a summation like that. Alright. If the sequence of partial sums has a limit, then the infinite series converges, and we can say that the limit as n approaches infinity of this thing, or put an infinity up at the top of our summation, is equal to whatever that limit is. If the sequence of partial sums diverges, the infinite series also diverges. Let's look at an example here. This is kind of a cool example. A sub n equals 0.9 times 0.1 to the n. So let's write out the partial sums. So what we want to look at is, do these partial sums, does the sequence of the partial sums converge or diverge? Does the infinite series have a solution? So in order to do that, the first thing we're going to need to do is write out the terms of the sequence itself. So we want to write out the terms of the sequence A sub n. Alright, so, and we're assuming here n equals 1, 2, 3. So if n equals 1, actually for this one, let's start at 0. It's going to be a little easier to work with. It's kind of the same deal, but let's start at 0. Okay, so if we let this be 0, we're going to get 0.9 times 1, that's 0.9. Okay, and if we let n equal 1, we're going to get 0.9 times 0.1, which is 0.09. If we let n equal 2, 0.1 squared is 0.01, or 1/100th, times 0.9. So it's just going to move the decimal 2 places. If we let n be 3, we get 0.1 to the third, which is 0.001 times 0.9 is just going to move the decimal 1 more place, etc. Okay, so that is A sub n. Now we want to look at the partial sums. So let's look at S1. So S1 is just the sum of the first term. Well, that's just one term. S2 is the sum of the first 2 terms. S3 is the sum of the first 3 terms. And S4 is the sum of the first 4 terms. Can you see what's going to happen here? And we could keep going. 0.09, 0.009, 0.0009. Alright, so our first term is 0.9. Our second term is 0.99. Second partial sum. Okay. Second term of our partial sums. The third term of our partial sums is 0.999. The fourth term is 0.9999. You can see what's going to happen here. Okay, so the sequence created by the partial sums, the sequence S, capital S sub n, is equal to 0.9, 0.99, etc. Does that converge or diverge? Hopefully you can see this is getting closer and closer and closer and closer to 1. So this converges to 1. All right. So what that means is that infinite series associated with A sub n converges. The sum from n equals 0 to infinity of A sub n is equal to 1. Or I could say, if I write it in this notation up here, the limit as n approaches infinity of the sum from n equals 0. Actually, I need to use a different variable here. Let's get rid of that n. Since I've already used n for my subscript, it doesn't matter what variable you pick. Let's pick j. That's a good one. Okay, so this j now is going to represent the upper bound of my summation. N is representing the terms in my sequence, a sub n. That equals 1. And we know it equals 1 because of this piece right here. Because the limit as n approaches infinity of the partial sums, which we saw over here, this limit of these guys is equal to 1, which is our L, our limit. Alright, let's look at one more example of these. This is kind of a fun one. Pretty basic sequence. A sub n equals 1/2 to the nth power for n equals 1, 2, 3, 4. Do you think the series converges or diverges? Okay, series, not the sequence, the series. So the sequence itself, a sub n, is going to be 1/2. If I let n equal 2, I get 1/4. So this is the sequence a sub n, 1/8, 1/16. Now, I agree, you're probably thinking, well, the sequence here does converge. I agree. The sequence converges to 0. But the question is, does the series converge? So to get the series, we have to look at the partial sums of this sequence. Okay, so s sub 1 is 1/2. S sub 2 equals 1/2 plus 1/4. I'll go ahead and write it out. 1/2 plus 1/4. That's 3/4. Okay, so we're generating a new sequence that's created by the terms of the partial sums. All right, this is our new sequence that we're looking at. And we want to know if this sequence of partial sums converges, which means the series converges. The series meaning adding up all the terms of a sub n. All right, so S3 is going to be 1/2 plus 1/4 plus 1/8. We're getting into some higher mathematics here. Let's see, that's 6/8 plus 1/8 would be 7/8. Okay, so our first partial sum was 1/2. Our second partial sum was 3/4. Our third partial sum is 7/8. Let's do one more. So our fourth partial sum would be 7/8 plus the next term, which is a 16th. So that's 14 16ths plus 1/16 is 15/16. What do you think this is going to converge to? Or do you think that this sequence converges? I hope you do. Let's see, the fifth one would be 15/16 plus the next term, which is 1/32. So that's 30 32nds plus 1/32 is 32 32nds. Matter of fact, we could probably write a formula for this thing right here. We could try. Looks like an interesting formula. Do you think it converges? I do too. It looks like it's getting closer and closer and closer to 1. So I would say this converges to 1, which means that the sum, let's just go to infinity. So we'll say from n equals 1 to infinity, instead of using a limit, of a sub n is equal to 1. If I add up all the terms in a sub n, I'm going to get closer and closer and closer to 1. This is actually kind of a classic series and sequence problem. A great way to visualize what's happening with these terms is to think about a box. So the area of this square, the whole square, this 1 by 1 square, the area of this whole thing is 1. So if I cut it in half and I just look at this shaded area, that shaded area is a half, which is our first partial sum. If I take the part that's not shaded and I cut that in half and shade half of that, I get a half plus a fourth, which is 3/4. All right, let's take what's not shaded and cut that in half. So here I have half the square, here I have a fourth of the square, here I have an eighth of a square. And what did that add up to be? 7/8. 7/8, yep. So now we have 7/8 of the square shaded. And we can continue this process. What do we got here? Here's half, quarter, eighth, a 16th of the square, a 32nd of the square, a 64th. All right, and we can see if we keep going and going and going and going, we're always going to have a little space that's not shaded, and then we're going to shade half of it, and then we're going to shade half of it. And if we keep doing this forever, you know, theoretically, we'll shade the whole square. Right? It's approaching 1. The limit is 1. The actual sum will never get to 1, but the limit is 1 of what the area could be when we add up all those terms. Okay, I know I think I said that was the last example, but I have one more because this one is pretty interesting. So I think you should go ahead and pause the video here and see if you can determine whether this series converges or diverges. All right, hopefully you've already done the work here because it's an interesting process to go through on your own. So I'm going to go through it, and so we're looking at the first 4 terms of the sequence of partial sums for this series here. So the actual a sub n that we're looking at, or a sub k in this case, is -1 to the k times k. So if we write out the first few terms, the first term would be -1 to the first times 1. The second term would be -1 squared times 2. -1 squared times 2. Yep, okay. Just checking my math here. Let's see, the third term would be -1 to the third, which is -1 times 3. The fourth term, -1 to the fourth, is positive. So we can see what's happening here. Looks like we've got -1, +2, -3, +4, -5, +6 forever. Alright, so our partial sums, our first sum is -1. Adding up the first 2 terms, we get 1. Adding up the first 3 terms, we get -1 plus 2 plus -3. That's -2. Adding up the first 4 terms, we're going to get -2 plus 4. That's going to be +2. The sum of the first 5 terms will be +2 plus -5, which is -3. The sum of the 6 terms is going to be -3 plus 6, which is +3. So this is interesting. Alright, so this list of partial sums creates the sequence -1, 1, -2, 2, -3, 3. Does that converge or diverge? Well, it certainly looks like it's not converging to anything. It's kind of an interesting pattern that comes out of this when you look at the sums. But hopefully you can see, you know, roughly it's going to look like, if this is S sub n, and this is n, you know, when n is 1, you get -1. When n is 2, you get +1. When n is 3, you get -2. When n is 4, you get +2, etc., -3. So you kind of get this kind of a thing happening like that. And certainly that's not converging on anything. So we would say it diverges. We could say it's divergent. The symbol for that a lot of people like to use is a D with a line through it like that. And similarly for convergent, if we say it converges to 1, we use a C with a line like that. This is a symbol for convergent and divergent. Alright, so in summation, no pun intended, in summary, if we think about what we've learned about sequence and series versus functions, there's a lot of similarities, but there's some differences, all right? And the big differences, for me, the big difference is the domain. So when we're talking about sequence and series, we're only going to use integers. Negative, we could start at n as a -1, that's fine, but we're never going to be looking at a half or square root of 2. We're not going to be plugging the square root of 2 in for n. But if you have a function, you could possibly have your potential set of x values is all real numbers. But if you have a sequence or a series, you have to look for your domain, so to speak, within the integers, right? Which again could include negatives. We haven't done one with negatives yet, but the integers do include negative numbers: -3, -2, -1, 0, and up. All right, and when we talk about adding up the terms of a sequence, we're looking at series, and then we're looking at accumulation. We're adding up the total. We're looking at sums. We're looking at sums. Whereas with functions, when we talk about adding up area or adding up what's under a curve, we're looking at an integral. So these two things are kind of analogous to each other. The big difference here is here you're adding up, you can kind of see the numbers that you're adding up. Here you can't, right? Because if you're doing the integral from 1 to 4, there are infinitely many numbers between 1 and 4. But if you're doing the summation from k equals 1 to 4, you're literally adding 4 numbers, and that's all you're adding. Now we could look at an integral from 0 to infinity, and that's an infinite, domain. We could also look at a sequence or a series from 0 to infinity. So now, yes, we're still adding up values, unlike an integral, but we're going to do it forever. So we're adding up an infinite number of values, and that's analogous to an integral from 0 to infinity. All right, well, I hope that video helped and that was a good introduction to sequence and series.